Okay, today we're going to look at what happens when we have moving charges inside of a magnetic field, or we could have a wire inside of creating a magnetic field. And we're going to look at what happens when certain scenarios occur. So we're going to be using our two formulas. Remember, we had magnetic force was QVB if it was a charge, and we had magnetic force was ILB if it was a wire. So both of those are going to be used, but now what we're going to look at today is combining it with some other sort of formula. So first off, let's figure out what happens when we have a charge in a magnetic field. So a little bit of a prelude. So we know our northern lights, we've talked about it before in class, but northern lights are just an example of charges from the sun being trapped in our magnetic field. So they hit our atmosphere, and they get funneled in at our north and south pole, and as they bump into air particles, they transfer energy, which gives off the light, and that's how we see the light kind of dance around. We don't see the funneling so much because the air currents that kind of blow them and distort them a little bit, but we do see sort of streaks and kind of zigzaggy lines. So the reason why it funnels and we get kind of this round circular motion is if we use our third hand rule. So in the bottom diagram here, we've got our electron going to the right, so point your thumb to the right. Our B is into the page, so your fingers would go downwards. So our force is to the south, so our force is going to be going southward. So in this second diagram, you can see that as soon as our electron enters the magnetic field, our force is downwards. So that means it's going to move the electron downwards. But then as it moves, if you sort of turn your hand, so move your thumb as it follows that curve, you can see that the force goes inwards as well. So really what ends up happening is as our electron goes around, the force keeps pulling it inwards, so basically it's going to go in a circular pattern. So because it's going in a circle, then we can say that our magnetic force is actually the exact same force as the centripetal force from Physics 20. So we can use those two things to help us solve these questions. So here's a question with some numbers now, but it's based on the same thing. We got an electron going in a circle. So the magnetic field causes it to go in a circle, so that means our QVB for the magnetic force has to equal our centripetal, which is mv squared over r. And you can see in the formula we've got a v on both sides, so let's cancel that. So one of the v's of the v squareds will cancel the other v, so we get QB equals mv over r. So the question here is asking, what's our radius? So we can move the radius up to the other side, bring the QB down, so we get radius equals mv over QB. So all we have to do is plug that in our formula and solve it. So we get our mass of electron, 9.11 to the negative 31. Our velocity is 2.38 to the 5. Our charge of an electron, 1.6 to the negative 19, and our magnetic field is 1.13 to the negative 5. So we put all that in the formula, crunch it out, we get a radius of 0.12 meters. Okay, so pretty easy calculation. You just have to make your two forces equal to each other and solve it for whatever variable you want. So the next example we're going to look at, or a couple different examples, we're going to look at what happens if our charges are balanced by gravity. So they don't have to always be circular motion. We can have our forces canceling out with each other and doing different things. So this first one I've got here, this first example, is we got an alpha particle being shot into a magnetic field at 90 degrees. So we have our magnetic field, and it says the magnetic force on the alpha particle is acting upwards. So we have our alpha, so let's draw that as a +2 charge. And it says the magnetic force is acting upwards. So it says determine the speed at which it must be traveling so that the magnetic forces balance out the force of gravity pulling it down. So as we shoot this thing in there, we really don't care about the directions of the magnetic fields or anything else. We just basically have to see that we got magnetic pushing it up, gravity pulling down. So if it's actually going to travel in a perfectly straight line, those two forces have to be equal. So we just basically make them two equal. So we'd have QVB again, equal to mass times gravity this time. And the question's asking what's its velocity. So you'd have mg divided by QB. So all you have to do is plug all those numbers in. So our mass for an alpha particle is 6.65 to the negative 27. Our gravity is 9.81. And our charge of alpha particle is 3.2. And our B in the question is 4.9 to the negative 9, or 4.9 to the negative 7. So plug all that in, crunch it out, and we get 0.42 meters per second. So it doesn't have to go very fast, but if you think about it, the force of gravity is pretty weak. The mass times the gravity on an alpha particle is pretty small. So we're not going to need a very quick velocity at all in order to balance out that force downwards. Example 3 on the bottom here is pretty much the same thing, except it says we have a wire. So now we have some sort of wire, and it says the current is going through the wire. So we have some sort of wire. Let me just draw it sort of as a in and out sort of thing. So we've got current going into the wire, and it says that current is pushing the wire upwards. So we've got a magnetic force pushing it up, and we've got gravity once again pulling it down. So it works out pretty much the exact same thing. The only thing that's different is when we use our formula this time, we're going to use ILB. So we'll have ILB equals mg. And the question is saying, what's the mass of the wire in order to get these things to balance out? So we just have mass would be ILB divided by gravity. So our I, I'll write it over on the side here, so our current is 7.81 to the negative 2. Our L is 0.298. And our B is 3.75 to the negative 3. And our G, 9.81. So we just divide those out, crunch those out, divide those out, and that'll give us a mass of 8.9 to the negative 6 kilograms. Okay, so it's pretty small, but once again, the gravity's not going to be very much, so we're not going to need much to push it upwards to balance it out. Okay, one last sort of example, and this one is where we're going to shoot our electron in again. So let's start with our electron, and we're going to be launching it horizontally. So it says we're going to set this up so our magnetic force and magnetic fields and electric forces sort of cancel each other out. So it says this time we have a charge plate of 250 volts, and they're 2 centimeters apart. So we're going to shoot this thing in, so let's suppose, and it really doesn't matter which way we do it, but they tell us in question A the top plate's positive, so let's use that. So if our electron gets shot into this plate, you can see that in the middle, once it gets somewhere in the middle here, it's going to be attracted to the positive plate. So our electric force will be going upwards. And then it says we've got a magnetic field, so in this case we'd have a coil, a wire, or something around the battery, something like that. And it says the magnetic force is it would have to be going downwards, right? If it's not going to deflect, if our electron's going to keep going perfectly straight through, then our two forces have to balance out. So in this case, we'd have magnetic force equal to electric force. That's really the only thing that's different. So first thing, let's go through a few of these. So if our electric field, it says direction of the electric field, so our electric field always goes from positive to negative. So electric field is going to be downwards, but we saw here that our electric force was upwards. Okay, direction of magnetic field. So if our force is downwards and our E is to the right, so that means our B then has to be into the page. So letter B we'd have inwards, which would be the X, right? And then part C is asking what's our velocity. So once again, we just use our formulas, QVB, but in this time for electric force, we just go Q times electric field. And you can see our Q's will cancel. So our velocity is a pretty easy calculation. It's just E divided by B. So all we have to do is do our electric field, which we don't know. right? But we do know that electric field equals voltage over distance. So they give us that. So if we go 250 divided by 2 centimeters, so 250 divided by 0.02, we get an answer of 12,500, and our B is 0.045, so divide that, and that gives us a velocity of 2.8 if we round it off, times 10 to the 5 meters per second. And that's it. So we got our different types of questions. So basically for each of these examples, our magnetic force was balanced either with circular, gravity, electric, some other type of force, and you just solve it accordingly.